Welcome to the AP Calculus BC video for skill number 227 and 228. Skill 227, I can find derivatives of exponential and logarithmic functions. And skill 228, I can use logarithmic differentiation. And the trivia question is, the graphic featured below is what and from what? Alright, for this skill, there's a couple quick differentiation rules we should refresh our brain on. The first is, when we're taking the derivative of a log, we find that all we have to do is write 1 divided by whatever we're taking the log of times ln of our base. And truthfully, this one doesn't appear all that often, but we can use it to create the derivative of ln of x. So what we have is 1 over x times ln of our base, which happens to be e, and ln of e cancels out, and that's how we get the derivative is 1 over x, in case you were curious. We can go one step further, and if we're doing the natural log of a function, we can apply the chain rule, and we find that the derivative of the natural log of that function is the derivative of the function over the function. So if I wanted to know the derivative of the natural log of sine x, then we find the derivative of the function, which is cosine x, and put it over the original function, which is sine x. And if I wanted to simplify that further, I would recognize that this is cotangent x. Alright, and the last bit of the page that we should note is less important for this lesson, but it actually has pretty significant implications later on in calculus. The derivative of the absolute value, the derivative of the natural log of the absolute value of x is also 1 over x. So if we have the absolute value bar, it's the same thing there. If you wanted to see a proof of this, it's in the textbook. You could split this into a piecewise function and take the derivative of both pieces, and you'd find that they both equal 1 over x. We won't use this, but it's worth noting because it comes back later on in calculus. What we really want to focus this lesson on is logarithmic differentiation. And calculation of complicated functions involving products, quotients, or powers can be simplified by taking logarithms. More specifically, derivative calculation. So maybe you want to write derivative calculation. And what I mean by products, quotients, and powers is like if we had x to the 7th times the square root of 2x minus 3 all over x to the 5th minus 4x to the 7th. What we have is lots of different powers in there, and products and quotients. And we could break this down as a chain rule of a product rule, of a quotient rule, and just do all of our rules, and we'd wind up getting some very nasty thing that we'd probably get lost in the process of trying to figure out where exactly it is. So what we have is logarithmic differentiation, which is a really fun, fascinating way to do differentiation. In fact, it's kind of one of my personal favorite methods for doing differentiation. In order to do it, we need to recall some of our properties of logarithms. And I wrote all of these as the natural log, but we could do it log base anything. Calculus tends to stick to using the natural log. And this first rule is the power rule, and it says if you have the natural log of something raised to a power, we can move the power down in front and get something that is equivalent. Similarly, on the second rule, if we have the natural log of a product of numbers, we can split that into the sum of two separate logarithms. And finally, if we had the natural log of a quotient of two numbers, we could split it into a difference of two logarithms. And these three properties are key to remembering if we want to be successful with logarithmic differentiation. So logarithmic differentiation, I've outlined the steps here, and I'll work through one example, but the way it works is in the first step we take the natural log of both sides, and then in step 2 we apply these log properties to expand our equation. Step 3, we differentiate implicitly with respect to x. So there we are relying on our ability to do implicit differentiation. And in step 4, we're going to continue that by solving for dy dx. And then step 5, if possible, substitute the explicit expression for y. In other words, if we started with our original equation, y equals, blah, 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 we can substitute that mess in anytime we have a y. So we'll see it in the example. It's very clear. This is on the next page. Alright, it says find the derivative for y equals x to the 2/3 times the square root of x to the third minus 2 all over 2x plus 5 to the 6th. Sure, we could apply the quotient rule, and within that apply the product rule, and within that apply the power rule and chain rule combined, and that would be all fine and dandy, but we'd probably get lost. So let's try logarithmic differentiation. Step 1 is take the natural log of both sides. So the natural log of y equals natural log of our explicit equation that we started with. In step 2, you're supposed to apply log properties to expand. So I was able to expand the product into an addition of 2 logs, and I was able to expand the quotient into a subtraction of the third one. From there, I use the power law, which allows us to take the exponents and move them down in front. So the 1/2 comes down in front, and the 6 comes down in front. What we have now is an expanded logarithmic expression. And in step 3, we're asked to differentiate implicitly with respect to x. So the derivative of ln of y is 1 over y dy dx. The derivative of a constant times ln of x is the constant times 1 over x. The derivative of a constant times ln of f of x is the constant times f prime over f, and the derivative of a constant times ln of g of x would be a constant times g prime over g. So that's going back to the chain rule with logarithms. Moving from this step down to this step, all I did was I kind of cleaned up my multiplications. For step 4, we're solving for dy dx. So in order to do that, I multiplied both sides by y, and that would cancel my y, and I'll multiply this side by y, and I find out that dy dx is equal to y times the equation that we had just figured out above. We could stop here with an implicit expression, but we would probably want to get an explicit expression. So our y here can be substituted with what we know y to be from above. So we take that y value and we plug it in, and you can see down below what I've done is I've plugged that y value back in right there. Everything else stays the same. I would not go further with simplifying this. At this point you've solved for dy dx, and that's good enough for AP tests, and probably good enough if you needed to plug in a value to evaluate what the slope of the tangent at a specific a value is. I only did one example because these are pretty long, drawn-out problems. Hopefully we'll get to work through some more in class. Alright, thanks for watching the video for skill number 227 and 228. The graphic featured below is a saddle from the game Minecraft. The saddle was first introduced as a pig saddle, and later on a horse saddle was added, and eventually they combined the horse saddle and pig saddle into one saddle, which is still, as of yet, uncraftable.